Yeah, so this is the 20th anniversary of what's now known as seL4. So 20 years puts us back to 93, which is the year that gave us the Pentium. It gave us Windows NT, and lucky or not, Win 11. And it is the year when Jochen Liedtke at SOSP talked about improving IPC by kernel design. So why is that a significant thing? What was there to be improved? Well, seL4 is a microkernel, and microkernels, the concept goes way back to 1970, Prince Hansen, etc. But they were really popularized in the 80s, starting with Mach. Everyone built microkernels. And then in the early 90s, there was this big disillusionment when people basically found that microkernels and systems built on top totally sucked. And at the core of this was what Liedtke called the 100 microsecond disaster. Basically, microkernel IPC operations, and that's of course the most fundamentally critical operation in a microkernel because it's used for obtaining any system service, they basically cost roughly 100 microseconds, almost independent on the actual kernel. And this performance number here for Mach is just representative. On a 486, running at 50 megahertz, 115 microseconds. And then Liedtke came with his kernel who did it 20 times faster. Now we had this morning the MIT paper about scalability. There were like factors of 20 or similar like that, where basically if you do scalability right, you can get improvements of this sort. But in a sort of a single core system, a factor of 20 in performance of fundamental system operations doesn't happen every day. So that was a reasonably significant event. And since then, microkernel IPC performance is pretty much what characterized seL4 kernels. And in a follow-up paper 2 years later, by analyzing a previously published performance analysis of Mach, Liedtke identified cache footprint as the main culprit that slowed down Mach and other previous microkernels. So since then, seL4 is known to be engineered for high IPC performance, and this has not changed in the 20 years. If we look at this table, which shows the performance of the IPC operation of various seL4 kernels, we can see in terms of cycles, it goes up and down. But that says more about the architectures and the kernels. Most of these were very highly optimized, and when they were slow in terms of cycles, that basically means that there was a very context switch unfriendly architecture. The one sticking out is the Pentium 4, which was really horrible. Opposite is the Itanium, which was really fast. And the overall trend is that as this processor's speed improves, the IPC costs go down. Very much in contrast to what Osterhout stated in his 91 Usenix paper, where he asked the question, why aren't operating systems becoming fast as hardware does? Because they basically were stationary. Okay, so question is, how was this achieved? And the most concise summary is by very strongly adhering to what's now being called the minimality principles of microkernel, first formulated by Liedtke 2 years after his original paper, SOSP 95, where he said the concept is tolerated inside the microkernel only if moving it outside the kernel, that is permitting competing implementations, would prevent the implementation of the system's required functionality. So basically, anything that doesn't have to be in the kernel should be thrown out. Interesting point to note is this comment about competing implementations. There was this view there might be a market where people sort of compete for the most efficient implementation of servers or whatever. That didn't quite happen that way. Nevertheless, minimality was the driver of seL4 development over the last 20 years. And this is summarized in this table, now, which shows lines of code for various seL4 implementations. Now, obviously, source lines of code is a very poor proxy for minimality of a design, but it's sort of the easiest one to look at. And it shows that things went up and down again. The ones where it went up were mostly kernels which had a lot of experimental features. But the latest kernel, seL4, with 10,000 lines of code, is not much bigger than the original kernel, and that was done by a serious masochist who like to shave single bytes off any bit of assembler code. And also, the seL4 number is somewhat overblown because for those who read our paper from 4 years ago, they may remember that the L4 implementation, the seL4 implementation, was done by a manual translation from Haskell. And that sort of gives bad operating system code, lots of small functions, etc. So the same functionality could be implemented in somewhere between 6,000 and 8,000 lines of code. And that sort of shows you that basically the kernel hasn't grown over 20 years. And this is extremely unusual for any kind of software system. And in terms of the APIs, they actually shrunk. They're overall much simpler than they were 20 years ago. Interestingly, this really sparked a lot of activities, and there's a large number of L4 kernels being built over the years. This family tree, which looks almost as complex as the one of Unix, only lists the more important ones. I've emitted a number of short-lived experimental versions. So it starts off with the original version, and that led to re-implementations on other architectures, and then a number of evolution steps which really changed a lot of the API without changing the basic model, and a number of commercial clones as well. And they actually got deployed in a number of mostly embedded applications. The very first commercial deployment was in the late 90s, an e-book reader. That was the Fiasco kernel. Then in 2006, Qualcomm adopted a L4 version as the basis for the firmware of their mobile chips, and in that way it ended up in several billion mobile phones. More recently, it's being designed into Korean trains, as well as the Airbus 350. This is the PikeOS commercial clone. The OKL4 kernel, besides secure phones, will end up in cars this year or next year. And the so-called Miracle phone, which is a Samsung S3-based secure phone, runs Fiasco. This is not the one the NSA hacked. The NSA hacked a version that didn't go through security approval. And probably also fairly well known is the verification. So seL4 is the first, and as to my knowledge, still only operating system kernel that has a complete verification from high-level security requirements, confidentiality and integrity, over several steps of refinement down to the binary. So there's a proof that the actual binary has these properties. And there's also unique, a complete and sound analysis of the timeliness of the kernel, making it suitable for hard real-time applications. Again, it's the only protected operating systems kernel that has gone through this. So this really gives you an indication that there is something to microkernels. They're good for something. And provided they are properly designed and implemented. And I'm going to have a bit of a look at what are the core implementation design features of the original kernel and how they fared over time. So in his 93 papers, Liedtke lists a whole bunch of implementation tricks which generally were pretty dear to his heart. And I'll go not through all of them, but some of them, and show how they fared. And similar in the follow-up paper 2 years ago, there was a lot of design principles he explained, and I'll have a look at how they fared. All of this was really driven by a minimality principle, of course, but also the desire to minimize cache and TLB footprint, because that had been identified as a shortcoming of earlier kernels. So let's start with some of the design aspects. And probably most defining feature other than IPC performance is the synchronous IPC model, this rendezvous model of message passing communication L4. So the idea is there's a send and a receive kind of operation, and in fact they're both merged into a single system call. And when two threads want to communicate, the first one reaching the IPC call blocks until the next one is ready. And at this rendezvous point, the kernel can directly copy data from the senders to the receiver's address space. So you get a single copy operation of the message passing. And the implementation of all L4 kernels I'm aware of always does this from the sender's context. So the kernel operating in the sender's context copies the data directly in the receiver's address space. And message data that is provided in registers actually can be passed by zero copy because they're just left in the registers during the context switch. So that basically the kernel does an incomplete context switch, leaving some registers intact, and this is a zero copy message transfer. So this is a basic model. The original L4 IPC was hideously complex, actually, and that was a simplification compared to Mach, if you read Jochen's papers. And one of these features there was what's called long IPC. It allowed you to send messages of arbitrarily aligned strings in memory to an arbitrary address specified by the receiver, of course, in the receiver's address space. And one of the implications of this is that if some of this data is unmapped, it will trigger page faults. And in order to do the operation, the kernel then needs to service this page fault somehow. The model in L4 is that page faults always get handled by user-level page fault handlers. So the kernel now, while in kernel mode, copying this data, catches an exception which requires it to invoke a page fault handler that's a user-level program. And that's actually a fair bit of complexity, right? You get L4 kernels generally run with interrupts disabled, so all concurrency is kept out of the kernel, which was really helpful when we verified seL4. In this case, we get concurrency back into the kernel because there's now user code executing concurrently with the kernel, and this user code has to do system calls in order to provide mappings. It also has the implication that, well, this page fault handler is a user-level program. It could be uncooperative and could just not do anything, in which case it would block the complete operation and would DOS the communication partner. So a client sending data to a server could DOS the server by just not handling page faults. In order to protect that, L4 had timeouts associated with these operations. And these added complexities as well. One of the things we learned over the years is this long IPC is not really necessary. We hardly ever used it. Because generally, if you have bulk data, you actually don't want a single copy either. Single copy is better than dual copy, but best is zero copy, so use a shared buffer, which is inevitably what most people use. It turns out that the really most strong reason for having this kind of functionality was to emulate POSIX-like interfaces, which really require you to copy buffers. Turns out these days, POSIX support is inevitably provided by running a Linux system in a virtual machine on top of the kernel, and any other specifically designed services have a more sensible API that basically uses shared buffer and doesn't require this functionality. So basically all the modern L4 implementations have simply unceremoniously dumped long IPC. So timeouts, I've already mentioned, they were a protection against denial of service, but in general, they are a protection for any kind of IPC operation because, again, a client does a blocking send followed by a receive to a server. If the server replies back with its request, then the client could just no, actually, this is not a protection. It's a protection for the client against the server, but that doesn't matter. There was a timeout provided in order to limit blocking at IPC operations. As many other things in L4, this was overloaded, so the timeout could also be used as a timed sleep by receiving from a non-existent thread. The problem with timeouts we found is no one had any clue on how to assign sensible timeout values. There's no real guidelines or procedures for picking timeout values. And when we, for example, ported a multi-threaded firmware stack from a well-known company operating in the mobile space that had 50 threads or something, all communicating via some form of IPC, assigning timeout values for these is basically a problem no one has an answer to. And in the end, inevitably, people used either 0 or infinity which basically means either polling and aborting if the partner is not ready, or blocking indefinitely. And obviously, the timed wait can be done with a separate system call by basically just providing a virtual timer device. So this is where there's not complete agreement in the community, but in all the Sydney originated kernel, we just dump timeouts and replace them by a single block or poll bit. Another thing we learned over time is the pure rendezvous model of IPC actually has serious drawbacks, in the sense that it forces a lot of complication on designs that are built on top of the kernel. For example, you naturally want to do something like this, where some thread initiates an I/O operation, keeps on processing, and then if it runs out of stuff to do, it synchronizes with the I/O and we blocks until it's done, or collect the result and continue. You can't easily do that with this rendezvous-based model. And in the end, effectively, you're forced into a multi-threaded design where you have a separate I/O thread whose whole purpose is just there to block until the the I/O is ready, and then you need to synchronize. So a multi-threaded approach using all the synchronization, which, as we all know, is very error-prone, is forced on logically relatively simple design. And of course, that is bad. People working on multi-core scalability also, of course, understand that a synchronous IPC model is very bad for that, because essentially it synchronizes execution of different cores. So we didn't quite replace this model, but we complemented it by what we call asynchronous notifications, which is a very limited form of asynchronous IPC. It basically allows a sender to send a message at arbitrary times without blocking to a receiver, and the receiver can either, as shown in the left part of this diagram, poll for the message or block for it. And the main challenge here is asynchronous IPC had been identified as one of the shortcomings of the original microkernel, in particular the need for the kernel to buffer data, and which not only implies double copying, it also implies a lot of bookkeeping, etc. We didn't want that, so we have a simpler model, which I'm going to explain in the next slide. But also, the model made it very easy to have a combination that allows you to wait on both a synchronous and an asynchronous IPC, which is pretty well suited for, say, a file server which has a synchronous client interface and an asynchronous interface where it receives essentially interrupts from devices. So, before I explain how this actually works, there's another issue that's relevant here, and this is the naming of IPC destinations. Original IL4 used thread IDs for directing IPC, and that has implications that basically it exposes the internal thread structure of a server to clients, which is bad. But it also forces unnecessary messaging. Basically, in order to either the load balancing has to be done by the client, which of course is bad, or the server internally needs to forward these messages, and that basically duplicates the number of IPC operations, which is also bad. So there's inefficient design, poor information hiding, but the killer argument was actually delivered by John Shapiro, who observed that these global thread IDs provide covert channels, and we didn't want that. So we moved to a model of port-like so-called endpoints, where instead of sending directly to a thread, you send to an endpoint, and each endpoint can have an arbitrary number of senders or receivers, anyone who has a capability to them. And this is also used for the asynchronous notification. They basically have a one-word map, which is where the data that is sent is deposited. So if some thread sends to the endpoint, its data gets ordered to this map, and it's a destructive thing. So if the receiver doesn't pick the data up quickly enough, it may lose it. Very much like interrupts. So this is a model that very nicely maps onto hardware interrupts and exceptions. There were other interesting things like the so-called clans and chiefs model, which was used for for example, enforce confinement, where a thread was restricted by a hierarchy from where it could directly send to, and if you try to send messages outside the hierarchy, they were delivered to its so-called chief, who can then forward it or not. That was probably the most cursed feature of L4. Anyone who was trying to build systems on L4 ran into that and basically hated it. And there was a closely related process hierarchy, which was also getting in the way all the time. It forces a lot of clumsy designs, and in the end, the proper way to do this kind of resource management or communication control is really by having capabilities. And so by introducing capabilities, we could junk all of that. Just before I run out of time, a little bit about implementations. L4 was full of implementation tricks, some quite ingenious. I'll just pick one of them or two. One was the kernel allocated thread control blocks in a large virtually mapped in a large array that was in virtual address space. And the advantage was you could find the thread control block by basically indexing in this array with the thread ID. Very fast. The cost, of course, is consumption of virtual address space as well as additional TLB entries. On the original x86, which had untagged TLB, that didn't matter because the TLB was flushed on the context switch anyway. Closely related was the idea of allocating the kernel stack with the thread control block. So the original L4 was a strictly process-oriented kernel. It had a kernel stack per thread, and that was allocated with a TCB. And so from a TCB, you could very easily find the base address of the stack by just masking in some bits, or the kernel from the presently executing thread could find the TCB by just masking off bits from the stack pointer. So very nice, fast. In this case, it trades TLB footprint for cache footprint, as well as, of course, kernel memory. And this really was the bad thing. We found that in some cases, or in many cases, pretty much half the kernel memory was tied up with these kernel stacks, and this didn't play too well in embedded systems. So we also did studies that investigated the performance trade-offs, and we found that these days actually it either doesn't matter or the original design is actually a disadvantage. So we got rid of that. We abandoned the virtual map TCBs and moved to an event kernel with a single kernel stack. I'll skip over the other nifty thing, which is lazy scheduling, which is a cool thing, but doesn't work that well, it turns out, and go back to this summary. So I already showed you that we basically abandoned a fair number of these original design and implementation features, and a few other ones which I didn't talk about. We also designed like non-portable implementation, which Jochen made a lot of fuss about. He violated calling convention. He did everything in assembler. The serial copy register messages turned out on modern processor, on an ARM, it buys you maybe 10% performance. On a 32-bit x86, it's actually detrimental because you take registers away from the compiler, and the compiler knows better how to use them. A recursive address space model is abandoned in some kernel, retained in others. But there's a few things that are still true, and one is non-preemptible implementations. There were actually experiments with fully preemptible kernels for real-time purposes. Turns out it's a bad idea. It just produces, it's costly in terms of all the critical sections you need to protect, and of course, huge source of concurrency bugs. User mode, page fault handlers are a very powerful thing. It's really a core mechanism for kernel, for policy mechanism separation. We retain those, and of course, user-level device drivers. So, looking back at now, from what we've learned over the 20 years, what really are the principles behind the design that have survived? And the most important one is clearly minimality. This really has, for the whole 20 years, been the driver for design decisions and really helped us to keep focused on keeping the system simple and fast. And it really resulted in the system becoming simpler over the years, which, as I said earlier, is a very unusual development. We really know now device drivers do belong at user level. Even Linux is coming around to that view slowly, but surely. IPC speed, even after 20 years, and a vast improvement in processor performance still matters. And we definitely saw that pretty much in all our commercial deployments, that you can't afford to throw away a factor of 2 IPC performance as a lot of other kernels do, or even worse. Most of our commercial deployments would just not have worked with if our IPC performance was significantly worse. It also, an interesting thing we found is that the verification of seL4 was not detrimental to IPC performance. seL4 is the fastest L4 kernel around, which probably makes it the fastest microkernel around. And we actually have learned that the invariants which we proved about during verification can help to improve performance. The paper was just given last week at UXLA. We definitely found capabilities are the way to go, so this was not in the original thing, but John Shapiro was definitely right about that. And we also found that we're still struggling to find a clean abstraction for time as a resource. And this is probably the last interesting problem at the kernel level the community is working on. So, all up, the design has changed, but the core principles remain. And well-designed microkernels definitely rock in my eyes. And some of the deployments and other developments, I think, prove us right there. Thank you very much.
Hi, Sudarshan, Georgia Tech. You mentioned that you talked about the user mode page handler. So do you lead up to a situation where you have to log the address space of the process? And if so, what is the point in doing it in user level instead of doing it in the kernel level?
So you have done what to the address space?
Yes.
Sorry.
So whenever you handle the page fault, do you end up in a situation of locking the entire address space of the process?
What do you mean locking?
If there are multiple cores that are trying to page to the same memory, so what will happen in that case?
Every address space just has one well-defined pager. Can't happen. There's only one page fault handler per address space, and that's the only one that is allowed to map.
So why does it have to happen at the user level instead of, because it's going to be generic? Why not at the kernel level?
Obviously, for every process, its pager is trusted. Sure. But that doesn't have to mean it has to be in the kernel. And in particular, just because you build a bad pager for your part of the subsystem, that shouldn't penalize me, right? I've got my own proper one.
Anton Bortsov, University of Utah. Oh, sorry. Get it. Okay, I'll continue. So, Gernot, like 10 years ago when I started with microkernel, you told me that the synchronous IPC is the way to go, and I believed you, truly. And now in this paper you tell me, well, not really, it didn't work that well. So we added asynchronous IPC. Well, and I again believe you, truly, but with a little smaller degree of trust. So the question is really, do you think we can go with this existing IPC, or we will really need to change it really to work something like similar to languages which can help us to build systems on top?
So obviously professors can be wrong as well, right?
I know.
This is actually an unsettled question. So I'm more unsure about the right model now than I was 10 years ago, and there is reasons to believe that maybe we should do away with synchronous IPC completely. There is one L4 kernel, the OKL4 microvisor, that does that. It has no synchronous IPC at all. Certainly it would better map to large multi-core designs. We might be heading that way. But of course this means more relying on shared memory, because you don't really have a payload anymore. So it's basically we all know that all you need is shared memory and semaphores, and asynchronous notifications are essentially semaphores. but it requires having a shared buffer.
Thank you.
Hello, I'm Volodymyr Kuznetsov, APFL. So one of the nice features of microkernels is fault isolations of the services. And now, fault isolations in particular benefits from state separation. Now with abandoning long IPC and switching to shared pages, you kind of make, you force a shared state between services that communicate through shared pages. So my question is, how does it?
Okay, yeah.
Okay.
Just because you don't have the kernel copying data for you doesn't mean you can't have a copying mechanism, right? It just has to be a mutually trusted server that does the copying, which is not logically from the security point of view or robustness point of view is not better or worse than having the kernel do it. It's a trusted instance. The kernel is a trusted instance, and you can have the same by having a trusted server that has access to both sides. In the end, in order to make it trusted, you have to have you basically have to make sure that it's trustworthy, but that's really not different from making the kernel itself trustworthy.
Okay, thank you.
Malte Schwarzkopf from the University of Cambridge. So you've commented a lot on sort of the evolutionary things that happened to L4, and I was wondering if you could also comment on a slightly higher level in what way these changes were influenced by maybe changes of the research/commercial agenda that L4 was pursuing. Because in the early days, it was very clearly sort of the mission was L4 microkernels in everything, you know, on alpha, on x86, on whatever. Nowadays, it seems to be much more targeted on embedded devices, sort of environments where you want formal verification. And there can be sort of cycles of cause and effect there, right? Because if you decide you want to formally verify, then maybe you change design decisions in order to make that easier. And yeah, I'd just be interested in hearing your perspective on sort of that level of the evolution.
So, yeah, you're right. I mean, we haven't really extensively tested it in non-embedded spaces because no one was too keen to deploy it there. I don't see any inherent reason why seL4 couldn't be a hypervisor for a cloud scenario. If we did it, we probably learned something about some of the design and implementation trade-offs that may be not optimal. But fundamentally, I don't think there's any reason to believe we got it totally wrong. But this is just based on, you sort of systems experience and gut feeling. There's no proof out there. But there's not a lot in the present, or there's nothing really in the present L4 design that is specific for embedded systems. It's just that there were the real-world deployment opportunity all happened there. From the implementation point of view, clearly there is a lot of implementation details that are optimized towards the kind of use case we're dealing with at present. I don't think from the basic design there's anything there. I could be wrong.
Thank you.
All right, thank you.